Okay, let's unpack this. Imagine you're a scientist, right? Standing near the end of the 19th century. For what, almost 2,000 years? Everyone just knew the atom was, well, indivisible, a tiny, solid ball. Dalton's whole theory was built on that idea. So your big challenge wasn't just finding a new element or something. It was basically overturning centuries of thinking, revealing that the atom actually had an internal structure, that it wasn't fundamental.
It really is like a detective story, isn't it? Playing out on scales we can barely imagine. And that's what our deep dive is about today, tracing that pretty radical path. We've looked at a whole lot of historical documents, research papers, basically charting the moment physics cracked open the atom.
Exactly. Our mission here is to follow those clues, one discovery after another. We want to show you how we eventually found these three tiny particles that make up, well, everything. And maybe more importantly, the big ideas, the breakthroughs that force scientists to just toss out their old models.
And here's the kicker, right at the start. The very fact that there were subatomic particles, that immediately showed Dalton's basic idea that atoms were uncuttable was just wrong. It started when they identified these tiny negative and positive charges within the supposedly solid atom.
So the first real crack in that solid sphere idea came from J.J. Thomson. His experiments, they essentially managed to pull out a negative charge from what seemed like neutral matter. That negative charge, we now call it the electron. And that was it, the moment the atom was officially, broken open.
But yeah, atoms are electrically neutral overall, right? So if Thomson finds something negative, there must be something positive lurking in there somewhere to balance it out. How did they track that down?
Ah, good question. That search for balance led to E. Goldstein and his discovery of Canal rays.
Yeah.
These were seen moving the opposite way to the electrons in his experiments. Our sources call them positively charged radiation streaming back through holes or canals in the cathode.
And what's really fascinating, even back then, was the sheer scale difference once they pinned down this positive thing, which eventually led to the proton. This proton, it's just massive compared to the electron, about 2,000 times heavier, give or take.
Wow, 2,000 times. Did they immediately think, okay, this huge positive thing must be the center? Or did that huge mass difference cause some confusion early on?
Initially, no, not really. They just knew they had these two pieces, the heavy positive bits and the super light negative bits. Before the third piece, the neutron, was found, the thinking was basically that the atom was just a jumble of protons and electrons mixed together somehow. They needed a model, a structure, to explain how they were mixed.
Right, which brings us neatly to the first proper attempt at a structure, Thomson's own idea. We usually call it the plum pudding model, or I guess a watermelon works too.
Yeah, it was quite an elegant idea for its time, trying to put the pieces together. Thomson basically pictured the electrons, the plums or seeds, just scattered randomly inside this single big sphere of positive charge, the pudding or the watermelon flesh.
And you have to give it credit where it's due. It did explain one really important thing, didn't it? It explained perfectly why atoms are neutral overall. The negative electrons just canceled out the positive pudding. Simple.
Simple, yes, but just a concept. It needed testing. And that's where Ernest Rutherford comes in, his alpha particle scattering experiment. Well, it completely changed the game. Possibly one of the most important experiments ever, really.
And the setup was key. Our sources mention he specifically used gold foil. Why gold?
Because you could hammer gold incredibly thin, just a few atoms thick sometimes. That was crucial.
Right, and then he fired these alpha particles, which are basically fast-moving helium ions, positively charged straight at this ultra-thin foil. What did Thomson's model predict would happen?
Well, according to the plum pudding idea, that positive charge was spread out so thinly, so diffusely, that these heavy, energetic alpha particles should have just punched right through. Maybe a tiny deflection, a little wobble, but nothing major.
And most of them did exactly that. They went straight through, just as expected, based on the empty space idea. But the real shocker, the thing that made everyone stop and think, was what happened to a few of them.
Exactly. Rutherford himself described it brilliantly. He said it was like firing a 15-inch shell at tissue paper and having it bounce back at you. It was unbelievable. About one in every, say, 12,000 alpha particles was deflected massively. Some came almost straight back.
Whoa. So what did that completely unexpected result tell them? What was the big takeaway?
Two huge things. First, the fact that most particles went straight through. That meant atoms weren't solid at all. It meant that most of the space inside an atom is actually empty, just void.
Okay, mostly empty space. And the second thing, the bouncing back.
That rare, violent deflection meant there had to be something incredibly small, incredibly dense, and positively charged right at the center. A nucleus. something dense enough and with enough positive charge to repel that incoming positive alpha particle so strongly. And nearly all the atom's mass had to be packed into this tiny spot.
And the scale of this, it's hard to grasp.
It really is. Rutherford calculated the nucleus's radius was about 100,000 times smaller than the whole atom's radius. Think of it like this. If the atom were a football stadium, the nucleus would be like a single pea sitting on the center spot. Mind-blowing, really.
Okay, so Rutherford gives us this amazing nuclear model. Protons jammed into a tiny nucleus, electrons whizzing around it like planets.
Yeah.
Revolutionary. But in solving one problem, he created a massive new one, right?
Ah, yes, the stability paradox. A huge headache. You see, according to the physics they knew then, classical electromagnetism, any charged particle moving in a circle, like an electron orbiting the nucleus, must continuously give off energy, like radiation.
Okay, so it's constantly losing energy as it orbits. What does classical physics say happens then?
It should slow down, spiral inwards really, really fast, and crash straight into the positive nucleus. Bang. Which meant, according to Rutherford's model plus existing physics, every single atom should collapse almost instantly. But obviously matter is stable. Things don't just implode. It was a major crisis for physics.
So they needed a fix, something that basically said the old rules don't apply here. And that fix came from Niels Bohr with a pretty radical quantum idea.
Exactly. Bohr's breakthrough was proposing something completely non-classical. He said electrons don't just orbit anywhere. They can only exist in specific, discrete orbits, or energy shells. And here's the crucial part for stability. While they are in one of these fixed orbits, they simply do not radiate energy. No spiraling death dive. That was the key insight. It broke the classical rule and explained why atoms are stable.
Okay, so Bohr saves the day, stability-wise. We have protons in the nucleus, electrons in these special stable orbits, sorted. But wait, there was still something off with the mass, wasn't there? Especially for heavier atoms.
That's right. Even with Bohr's model, when scientists actually weighed atoms, the mass didn't quite add up. If you just counted the protons, the total mass was always a bit too low, especially for elements beyond hydrogen. There was missing mass in the nucleus.
Which implied there must be something else in there.
Precisely. Something with mass, but no electrical charge. Otherwise, they would have detected its charge effects earlier. That missing piece was the puzzle J. Chadwick set out to solve.
And he found it. In 1932, Chadwick discovered the neutron.
Yes, the neutron.
Right.
No charge, as the name suggests, but crucially, its mass is almost exactly the same as a proton's mass.
So that's the missing weight.
Exactly. With the neutron, the picture was finally complete. The mass of an atom is basically the sum of the masses of its protons and neutrons.
Yeah.
And because they live together in the nucleus, protons and neutrons are often collectively called nucleons. Right, so now we have all the building blocks, protons, neutrons, electrons. We can finally look at the blueprint that defines what an element actually is, the absolute core identity. That's defined by the atomic number, which is simply the number of protons in the nucleus. That number is the element. Then you have the mass number, which is just the total count of protons plus neutrons, the total number of nucleons.
Okay, protons define the element. Neutrons add mass. What about the electrons? Where do they fit in? You mentioned Bohr's shells.
Yes, the Bohr scheme helps organize them. There's a simple formula, 2n squared, where n is the shell number, starting from 1 closest to the nucleus. This tells you the maximum number of electrons that can physically fit into each shell.
So like the first shell, N1, holds 2 times 1 squared, which is 2 electrons. The second shell, N2, holds 2 times 2 squared, 8 electrons.
Exactly. That formula sets the capacity. But the really important driver for chemistry, for how atoms interact, is stability. Inner shells fill it first. But the ultimate goal for most atoms, especially in the outermost shell, is to get to a stable configuration, usually 8 electrons. We call that the octet rule.
And those electrons in that outermost shell, they're the key players, right? The valence electrons.
Absolutely. They dictate everything about how an atom behaves chemically, whether it wants to bond, react, share electrons, steal them. Think of valency as like the atom's desire to reach that stable octet.
Can you give an example?
Sure. Take sodium. It has 11 electrons. Its configuration is 2 in the first shell, 8 in the second, and just 1 lonely electron in the third, outermost shell. So its valency is 1. It's much, much easier for sodium to just give away that 1 electron, leaving it with a stable, full second shell, than to try and gain 7 more.
Ah, okay. And what about something on the other side, like fluorine?
Fluorine has 9 electrons. That's 2 in the first shell and 7 in the second outermost shell. It's so close to a stable octet, it desperately wants to gain one more electron. So its valency is also effectively 1, but in the sense of needing one electron, you find its valency often by subtracting from 8. So 8 minus 7 is 1. This strong desire to gain an electron makes fluorine extremely reactive. That drive for the stable octet fuels all of chemistry, really.
Okay, this structure makes sense. Protons set the identity, electrons rule the behavior. But it does raise a question. If the number of protons is fixed for an element, what happens if atoms of the same element have maybe a different number of neutrons? Does that happen?
It absolutely does. And that's what isotopes are. Isotopes are atoms of the very same element. So they have the same atomic number, same number of protons, and therefore the same chemical behavior, but they have different mass numbers. Why? Because they have a different number of neutrons in the nucleus.
Ah, like different versions of the same element. The famous example is hydrogen, isn't it?
Exactly. You have normal hydrogen, called protium, which is just one proton and one electron, no neutrons usually. Then there's deuterium, which has one proton and one neutron, still hydrogen, but heavier. And tritium, with one proton and two neutrons. Chemically, they all behave like hydrogen, but their masses are different.
And these differences matter in the real world, right? It's not just theoretical.
Oh, hugely. That difference in neutron count can be critical. For instance, a specific isotope of uranium, uranium-235, is one used as fuel in most nuclear reactors. Other uranium isotopes exist, but that small difference in neutron count makes U-235 suitable for sustaining a nuclear chain reaction. It's fundamental to nuclear energy.
Okay, so isotopes are like variations within the same elemental family. What about isobars? That sounds similar but different.
Isobars are a bit different, yeah. Think of them maybe as neighbors rather than family. Isobars are atoms that actually have the same mass number, meaning the total count of protons plus neutrons is identical, but they have different atomic numbers.
Wait, if they have different atomic numbers, they must be different elements entirely.
Correct. They just happen to weigh the same or have the same total number of nucleons. A good example from our sources is argon, which has atomic number 18, and calcium, atomic number 20. They're completely different elements. But one common isotope of argon, argon-40, and the most common isotope of calcium, calcium-40, both have a mass number of 40. So argon-40 and calcium-40 are isobars. Same total mass, different identity. Hashtag tag outro.
Wow, what a journey we've traced. From thinking atoms were these tiny, solid, unbreakable balls, to Rutherford showing us they're almost entirely empty space with this incredibly dense nucleus, then Bohr having to kind of bend the rules of physics to make that model stable.
And finally, Chadwick finding that last crucial piece, the neutron, to make the mass and the stability of the nucleus finally add up. The whole field just transformed in, what, maybe 30 or 40 years, from ancient philosophy almost to hard physics. And now we know. Identity comes from protons. Behavior comes from those outer electrons chasing stability.
We mentioned at the start how finding electrons and protons really broke Dalton's old indivisible theory. But it strikes me now that finding the neutron, that neutral particle Chadwick discovered, was just as profound. It didn't just solve the mass puzzle. It's crucial for holding the nucleus together against the repulsion of all those positive protons.
Absolutely essential for stability, especially in heavier elements. And of course, the neutron is the key player in nuclear fission and fusion.
Right, so here's something for you, our listener, to think about. We know neutrons are vital for nuclear stability and for the chain reactions that power nuclear energy, or are used in medical treatments and imaging. How much of our modern world, our technology, our medicine, how much of it would simply not exist, would be impossible if Chadwick hadn't found that quiet, neutral particle back in 1932. What would the 21st century look like without the neutron? That's quite a thought to ponder.